Welcome to another decommissioning podcast by the Curtin University Oil and Gas Innovation Center. Today we hear from Christopher Murphy about Riserless Deepwater well decommissioning. Over to you, Chris. Thank you.
Well, thank you, Klaus, for that introduction. So welcome everybody. I'm Chris Murphy. I'm a Senior Research Fellow at Curtin University Oil and Gas Innovation Center. And today we're talking about Riserless Deepwater well decommissioning. So for clarity, it's always good to have definitions. Riserless means working on a subsea well without the use of a conventional drilling or workover riser. And therefore the only means of accessing the well is using wireline and fluid circulating systems. Our well decommissioning, as we heard from the previous webinar, used to be referred to as well abandonment or permanent well abandonment or P&A, but the newer terminology is well decommissioning. In terms of wet or dry trees, the main difference is clearly the access method. A dry tree is on a platform or on land, and a wet tree is underwater. So with a dry tree, very simple, you can rig up with a drilling rig, workover rig, hydraulic workover unit, coil, or you can use wireline and pumping, which is the more preferred method from a cost perspective because you can then apply rigless techniques to the dry tree wells. With subsea, especially deep water, the fundamental difference is you have to have a vessel of some description, and from that vessel you then need to launch specialist equipment that allows you to make a pressure connection to the top of the tree, whether it's vertical or horizontal, so that you have well control during your deep water well decommissioning operations. We know we need a vessel, so let's understand what those vessel types could be. And we've taken here it's Statoil as a source. It's the Norwegian continental shelf categories of vessels to access wells. And so Cat A is quite often a monohull, and the capabilities are usually interfacing with the tree with a subsea intervention system and the capability to run wireline. Now Cat B can be a small semi-sub or a monohull, but the difference is it can riser up with a high pressure, rather small ID riser, but it can do a little bit more with through tubing access. Now Cat C are your standard drilling rigs developed by the drilling contractors. It can be semis, drill ships, ultra deep water drill ships, deep water jackups, and we'll only be talking about the first three categories in this particular webinar. But for interest, Cat D is what Statoil classes a workhorse semi, and its basic aim is for production drilling and completion operations up to the ice edge. Cat I is currently in development, but it's a very harsh environment, Arctic drill ship. And Cat J is again, it's a workhorse jackup for water depths between 70 and 150 meters, and it's specifically targeted at harsh environments, which is very prevalent offshore Norway. Now, as always in the oil and gas industry, nothing's quite black and white, but let's just, for the sake of clarity, just define pictorially what those classifications for the first three cats are. So you've got rigless light well intervention, normally a monohull, left hand side of the graphic, and it's wireline. Obviously you can run tractors on electric line. Very short BHAs because they're limited by the length of the riser above the subsea intervention system. Cat B is for slightly heavier intervention and through tubing access. Normally there's a small bore riser which gives you full pressure access to the well, and you can do quite a reasonable range of through tubing services. And Cat C, which is your normal drilling and completion rigs, semis or drill ships, and they've got a standard set of large bore, usually 18 3/4 VOPs, and then above that you've got the low pressure, normally a 21-inch standard riser. You can riser up with a concentric high pressure and a subsea test tree if you want to do live well intervention, but we won't be discussing that here because it's rather an expensive exercise and it's not targeted specifically at well decommissioning in deep water. So in a deep water well decommissioning environment, you have to consider a myriad of different variables, but let's just look at a short list. So you have to define corporately what your decom strategy is. Is it to look at the operation, say we'd like to execute to satisfy our corporate and our regulatory body, but we'd like to use a riserless method? Great. Or we'd like to go riser because we're more confident that that's what we'll need because there are problems with wells. That's possible. Are you looking at caprock restoration? A lot of companies are now looking at this because of the significant cost and time savings. It may or may not be applicable to your organization, but certainly it's definitely worth pursuing if you have the opportunity. So when you look at vessel type, that comes from, are you risering up or are you trying to go riserless? Well complexity obviously plays a great part in this. Water depth plays a great part too. And never forget that the economics drives everything. So no matter what you decide, it'll be the financials that come out to take it forward to an investment decision to proceed. Now, with respect to complexity of completion design, there are some things to keep in mind. In the newer deep water wells, there can often be chemical injection lines going deep into the well. There can also be electric lines, and some of the regulations indicate that it's best practice not to include those within a well barrier element. Although there is research being conducted in the last few years that indicates that perhaps that's not quite as big of an issue as people thought it was with respect to microannulus formation around those umbilicals and electric lines. Now, another thing that's important is that you have access to a good quality cement evaluation log, especially across the caprock formations, because that's probably what you want to target for cost reductions in the overall scope. And if you don't have that, it almost precludes your doing a well decommissioning in a riserless environment. Hydrate's always a problem, and when you get into deep water, you have to have a plan in place, and there have been a lot of train wrecks because people haven't understood the massive problems hydrates can cause. So have a plan in place for that. Another interesting one, which you don't always think about, but when you're looking at going into a subsea development for cessation of production, so you're abandoning all the wells, so decommissioning now is in full swing, the reservoirs are normally significantly under pressure, and in actual fact you can have vacuum conditions with the seawater column. So bear that in mind, because it can make accessing the well, especially if you're in a horizontal tree environment where you're pulling plugs from the top of the tree, you can have a lot of problems with that with the vacuum condition. And of course, the single most important, depending on which regulatory body you're working with and what your corporate guidelines say, is the blind annular isolation and verification, which until a few years ago was extremely difficult to accomplish without the use of a rig and going in and milling casing, etc. So that's a very, very short list. It by no means tries to cover the whole spectrum of things to be considered, but these are really, really important pieces. Blind annulus isolation is a very big topic. How do you know if you have sustained casing pressure in a blind annulus? Well, the answer is you don't know, because for the life of that well, and because of the design of the wellhead, the only annulus you can monitor is between the production tubing and the production casing, which is classed as the A annulus. And there are one or two very specialist wellheads that have been developed in the last few years to do more than just the annulus monitoring, but they're very, very rare. So how will you manage subsea well decom with blind annulus isolation, or blind annuli being the plural, if your regulatory scheme prescribes that you have to verify that there is a barrier in place and it's tested or it's verified? That's a complicated problem which normally in the past has required the use of a rig. So the US regulations are very explicit with respect to this annulus space that communicates with open hole and extends to the mudline. And it says in the Code of Federal Regulations in section 250.1715 that a cement plug of at least 200 feet has to be set in the annulus space. It does refer to a well completed above the ocean surface, but working with the BSEE organization, they also apply this to subsea wells, and a lot of oil and gas companies with significant numbers of assets in the Gulf of Mexico apply the same thing. So that requires the use, or prior to a few years ago, always required the use of a big rig to isolate those blind annuli. So you have to look at, do your corporate guidelines require annular isolation? And if so, how will you perform it? Because it can be done, clearly it can be done with a big rig, but it does get to be exceedingly expensive. So in the hypothetical case study, we've made it really simple. It's deepwater riserless well decom, and we put a lot of boundaries into it. So we said it's a multi-well campaign, 2,000 meters of water depth. The wells must meet annular isolation regulations. The cost for a Cat C vessel is estimated at approximately 30 million Australian dollars per well. So that's access with a big rig. The cost to access the well with a Cat A vessel is estimated at $15 million per well, which is a rigless operation. Now, well decommissioning activities are common practice irrespective if the well is underwater or it's at surface. So they will not be covered in this case study, or in fact in this webinar, because they were already covered in detail in the rigless well decommissioning webinar, which was webinar before this one. So if you get a chance, please go look at that, and bear in mind everything you see there is applicable to deep water wells. Now, all engineering work has been finished and the company have elected to execute the project riserless. So never underestimate the amount of work required to get to this stage. We've made it look really simple, but this is multiple months, if not more, of extremely detailed engineering work. So we know we need a vessel, which is absolutely mission critical, but also mission critical is in a subsea deep water environment is a well intervention system, and we've used a graphic here. It's sourced from Technique FMC, and it's very pictorial and very simple, and it says, right, we need a pressure control head for our wire line, whether it's slick line or electric line. We need a lubricator to run tools into the well under a full well control situation. We have a lower lubricator package which allows us to close in the well and install tools and then lock on the pressure control head and then reopen the lower lubricator package. And we've obviously got a full well control package with shear capabilities. And for a riserless well intervention, we have to have circulation. Now, it's not shown on this diagram, but they do have a module they can apply to this to give you full circulation, and several other companies who provide this type of equipment have got circulation systems. And so if you look at the right hand side, you remember that's one of the graphics previously. That yellow piece in the middle of our graphic is below the category A rigless light well intervention vessel, shown sitting on top of the tree on the seafloor. So we are in a hypothetical study which specified a Cat A vessel. And pretty much everybody who's been around subsea well decommissioning will recognize a vessel like this. It's very common. It's got its own work tower. It's a DP2 or normally DP3 with work class ROVs, etc. And so that's obviously what we'll be looking at. But just bear in mind that outside of this particular case study, that doesn't look like a Cat A vessel. That looks like a Cat C, right? But if the market, as it is right now, unfortunately, very low oil prices, and so the rig market is extremely dire, you can, possibly in the future, if you're embarking on a rigless operation, you might be able to secure a very large DP semi for little more than the cost of a standard Cat A vessel. So bear in mind there are some advantages to this, in fact significant advantages insofar as You have very large deck spaces, you've got DP3, you've got normally better weather capabilities than a monohull vessel. So don't rule out using a big rig simply because you think the prices are escalated significantly higher than a conventional Cat A, because in a low oil price environment that might not be the case. So we start with the end in mind, and we'll restore the caprock because it's a hypothetical case study, and it's by far the preferential method for reducing the cost for any well decommissioning, whether it's a dry tree or wet tree. So we'll install our secondary and primary barriers in the caprock. Remember, because it's a subsea study that we have stated previously, we did need access to a cement evaluation log, and the reference in this case is you have to have good quality bond across the caprock for a minimum length. We've said in this case it's at least 200 meters because we'll place two primary secondary barriers, each of 100 meters in length, and we'll place those at the caprock, and we won't isolate the lower part of the completion because our subsurface teams have already decided that there will be no detrimental effect over geological time. So how we'll do this is quite simple. We won't go into the nitty-gritty of it, but we'll perforate the tubing string, we'll then circulate the well, and we'll circulate our barrier material, which is normally cement, into the down the tubing into the annulus, and we'll do that twice, and we'll have a primary and a secondary barrier in place. So that previous slide basically was Riserless Deepwater well decommissioning at the reservoir level. But the next step is intermediate barriers, which is again relatively simple, and it does require the same information set, that being a cement evaluation log across the impermeable rock above any aquifer and or other hydrocarbon zones in the well of a minimum length, and in our case we've said it's 200 meters because we're setting a primary secondary barrier envelope across that part of the well. And we do exactly the same thing. We wireline perforate the tubing string, then we circulate each of those barriers into place, and we pressure test those barriers, and we do that independently to the primary. Then we set the second barrier, and we are good to go on the next part of the well. Bear in mind again that in the previous webinar we talked about slumping of barrier material, so that's been considered, but you should consider that independently if you are actually embarking on a real decommissioning deepwater program. So now the final step, and in a riserless deepwater well decommissioning operation, this is normally being done with a big rig, but in our case we've elected to do the whole project riserless, and so that means we're not using a big rig for its large rig capabilities and tubing handling and milling capabilities. We might be using it as a staging point for our subsea intervention system, but we're going to do this riserless, and we have to accomplish this in the case study in order to get acceptance from the regulatory body that the well has been isolated to a satisfactory requirement, which means that annular barriers are placed and tested. And if that's not the case, if we don't manage to do that, this well will remain on the books as a liability on the balance sheet until such times as we go back with the big rig and actually execute that program for installing those barriers. So how's this done in a riserless environment? This is the thing that a lot of people many years ago said we couldn't do, but it has been done, and we'll go through how it's done. So first off, bear in mind you've got in the center of the wellbore, below that bridge plug, you have a production tubing which has been cut, and the upper part of that tubing, including the surface control subsurface safety valve, has been pulled open water. The well is already dead and isolated, and the lower part of the well is classed as already permanently abandoned, so we can pull this open water. We have a B annulus on this study that's open, and that was designed in the well design because of thermal effects, so we know it's there. And likewise a C annulus, also open because of thermal effects for the well. So we now need to set a B annulus barrier and a C annulus barrier, and that means we have to install barrier material into each of those annuli independently and test it. So the reason why you're probably watching this webinar is to find out how can we isolate those blind annulus in a riserless environment, subsea, deep water. So we need a subsea well intervention system, which is the large yellow equipment that we saw on previous slides. Below that we have a tubing string of a certain dimension, depends on the well geometry. We have a work string which has got a packer at the base, and that can be actuated, so we can isolate the well above the packer and below the packer from a pressure perspective. And above the packer there are a set of annular fire perforation guns, and we'll go through why we need this shortly. We have an open B annulus. We are now going to wireline perforate the casing through the work string below the production packer, and we're going to perforate the casing above the packer using the annular fire systems, and you'll see what happens next. We've now got a circulation path. If we were to pump down through the subsea well intervention system through the work string, out of the work string and down to the perforations, it will go back up the open annulus and come back to us into the wellbore, which is all pressure control because we're sitting on top of the large bore wellhead connector. So we've got full well control through the well intervention system, and we can take returns above the packer, and we can circulate till we feel comfortable that we've got clean and uniform fluids throughout that annulus. And because we've now got circulation and we understand the exact geometries, we can place that B annulus barrier. So we pump down through the tubing string into the casing, we displace it such that we end up with a plug through the perforations, which is uniform across the internal part of the production casing and the B annulus. This is super simplified. We've talked about slumping material. You may have to make 2 runs with perforation guns. The first run to set the material to stop the slumping of the material in the main wellbore, and then come back and set a second set of perforations, do the plug. But for simplicity's sake, we've said we are going to do some methodology for anti-slumping. So we've now got the B annulus completely isolated and tested, and we've pressure tested positively and negatively. We can do that, and we've also tagged the top of that barrier with wireline coming through the work string. So now we have an open C annulus we have to address. And how do we do this? Because this is a bit more complex because there are 2 annuli as opposed to 1. So we'll do the same thing. We'll perforate the production casing, but this time we'll perforate through 2 strings of casing, and the perforation technology is extremely advanced, and don't think that you can't do this without damaging that 3rd string, because it's eminently feasible and it's been proved multiple times. You can design specific charges to only perforate through whichever casing strings you happen to have in your well in any geometric configuration, whether they're concentric or otherwise, and not damage that 3rd string such that you've got a pressure problem, because that's not advisable nor wanted. We've already got the B and C completely isolated, and now we're looking at an environmental barrier which we normally would set inside the production casing string, and we would set just above the perforations that we used, which was sitting originally above the work string packer, to isolate those into the center wellbore. So we've verified the barriers by wireline tagging the top of the barrier inside the production casing, as I said. And we've now also got positive pressure tests, and you can also apply negative pressure tests, which some companies like, through the production casing and the annuli independently, because it's a separate system isolated by that packer on the work string. Now, there is a patent for this methodology using this system. There are other systems that have been used in shallow water environments, which normally don't use a packer. They use possibly inflatables and or cup type tester systems. So they've been applied in the North Sea, but this particular system here is a method patent, and you can go look it up if you so choose. So in this case, the riserless well decom actually could save us 50% or more of the existing operator well decommissioning estimates using a big rig. We went through a constraint-bounded hypothetical case, but there was actually a work program conducted in the Gulf of Mexico, and the operator was Marubeni Oil and Gas. And in 2016, they decommissioned 9 deepwater wells, and they only used wireline and pumping, and they met all BSEE regulations on the complete well decommissioning process, including the blind annulus isolation. And in some wells they did 1 blind annulus, in some wells they did 2, and in one well they did multiples of the blind annulus process. So it's a great article. It was presented at a conference. This article is still available. There's a link at the bottom, and you may find it interesting reading. But it has been done, so the track record is there, the precedent is set. So if people say you can't do it riserless, then point them to this article, because it clearly can be done and was done and was successfully accomplished. And a very large proportion of the estimated time was saved, and of course that equates directly to saved costs. To close out the deepwater riserless well decommissioning, there's no question that the simplest part is the deep well decommissioning process, which is the caprock restoration in this particular case. Absolutely no question that the devil is in the details when it comes to deepwater riserless blind annuli or annulus isolation. There's no doubt it's possible, it's been done, but it is a complicated issue. But if you can crack that difficult nut, there are some huge gains in terms of time and cost, because you can do the complete well decommissioning process without accessing the well with a big rig. So if you are looking at or considering deepwater well decommissioning, and you are in the place that says you have to have blind annulus or annuli isolation and verification, refer back to this, but don't use this as the gospel. This is high level, very short 30-minute presentation, but it's been done, and you can do it too if you contacted the right individuals. So once again, I'd like to thank everybody for participating in the webinar, and all those that helped to peer review. It was quite a lot of fun putting it together. It's an interesting subject, and it's a big subject for the industry. But we hope you enjoyed it, and we hope it's food for thought. Again, if you want to contact us, there are links on this particular slide, and I'd just like to say thank you very much, and hope you follow us and look out for more webinars in the future.